Hello and welcome to another adventure of the New York City Category Theory Seminar. Today we have Andrei Rodin, who's, I think you've spoken 3 or 4 times by us. Anyways, he's going to talk about Kolmogorov's calculus of problems and homotopy type theory. Take it away, Andrei. Andrei is now in France, no longer in St. Petersburg. Okay, take it away.
Thank you very much, Nazan, and thank you very much for inviting me, for having me here. So indeed, I'm going to talk about Kolmogorov calculus of problems. That actually his paper of 1932, and I'm going to make some connections with homotopy type theory. Okay. So plan is just I would call about problems and theorems. That is a very old topic, traditional from Euclid and Proclus, but I'm not going to talk about this longest history, only about Kolmogorov and more recent developments. Then I more specifically will talk about constructive negation, the idea of negated problem in Kolmogorov. And I'm going actually to argue that there is something that is not yet probably well formalized and could be motivation for interesting further work. Basically, that's my two things. Okay, so that's the paper. So actually, Kolmogorov had not so many logical papers, basically 2. One was earlier in 1925, and that was on interpretation of classical logic in intuitionistic logic. But that was published, earlier paper published in Russian and very little known. And on the contrary, that paper was published in a leading mathematical journal of the time. So he was somehow in the center of discussion with Heyting and other people. And a bit later, I'll actually I'll refer to this discussion. There are letters exchanged with between Kolmogorov and Heyting. So I'm going to briefly talk about also, take some materials from these letters. Okay, now I just very short exposition what he means by calculus of problems, what is the idea of the paper. So just have some quotes here. So what Andrei Nikolaevich says that along with the development of theoretical logic, which systematizes the schemes of proof of theoretical results, it is also possible to systematize the schemes of solutions of problems. For example, geometric construction problems. If we can reduce the solution of problem B to the solution problem A and the solution problem C to solution problem, C to solution of problem should be B, then the solution of C can be also reduced to solution of A. So we have this relation of reduction between problems, which is similar to, say, logical consequence, and we have this analog, say, of modus ponens for problems. That's the idea. And then he claims that the following remarkable fact holds: the calculus of problems coincides in form with Brouwerian logic recently formalized by Heyting. And here he makes reference to a big paper of 1930, which was published in 2 parts. By Heyting. So there is actually very interesting material also in that paper, but I think I leave it inside because otherwise it would be too long. Then he actually makes even a stronger claim that he says that provided that the general intuitionistic presuppositions are accepted, the intuitionistic logic should be replaced by the calculus of problems. So he doesn't just think about this calculus of problem as a possible reading of Heyting's calculus. He really insists that it should be read the way he proposes. Okay, and there is naturally a question which is still debated, I would say, but that is historical debate, that is this difference between Kolmogorov proposed interpretation of Heyting calculus, and Heyting calculus is basically propositional intuitionistic logic in a standard today sense. So is his proposed interpretation in terms of problem and Heyting's interpretation in terms of propositions somehow essential, or it's merely linguistic difference, whether we call these things problems or propositions. And I recently had a very long discussion with Mark Van Atten, who is a really serious historian of all intuitionistic mathematics. He had a long article on Stanford Encyclopedia of Philosophy about history. So actually, Mark, I think he tries to defend kind of, I would say, orthodox, maybe intuitionistic point, according to which actually the difference exists, but it is, in a sense, superficial, right? There is, according to Mark, and actually I'm going to discuss this viewpoint more seriously because also, say, Per Martin Löf, at least in his earlier writings, he also defended that point that basically there is kind of generic notion of proposition intuitionistic, which is rather different from classical, which actually allows to see these problems as a just kind of proposition in this intuitionistic sense. Okay, so and that's actually what going in under so-called BHK interpretation. So BHK interpretation, BHK today, it's kind of thing used for teaching about, for semantics of intuitionistic logic. So it's kind of proof-based interpretation. For example, you interpret implication by saying A implies B. That means that solution of problem A, if you have a solution of problem A, so that gives you a solution of problem B. So that's interpretation works either in terms of solution or in terms of proofs. So if you have proof of A, that gives you proof of B, and that's how you explain implication, and similarly with other connectives. And that was introduced in 1997 by Dutch logician and historian of logic, Troelstra. And actually interesting that originally this K stood for Kreisel. And later somehow, that's, I didn't look precisely in which circumstances, I'm not sure that the precise account exists or could exist, I simply don't know. It's a kind of change for Kolmogorov. So today, normally people would, by BHK, mean Kolmogorov and not Kreisel. So I'm going actually to say that there are still important differences, right, between Kolmogorov and Heyting. So this idea to put all them together, it's, say, controversial, but it expresses this idea that, say, just Kolmogorov stressed one aspect of the structure, and say Brouwer and Heyting another aspect, so somehow these things well integrate together. I rather try to argue that there are some real and interesting tensions between, say, Kolmogorov's view and Heyting's view. Okay. But actually, as I say, it's very interesting look closer into Heyting and Brouwer, but it's not what I'm going to do now. And to represent that view that I would call kind of orthodox intuitionistic, I rather refer to Per Martin Löf, and that's actually also bring us closer to type theory and homotopy type theory. And the Martin Löf, I'm going to use his early version of his type theory. It was lectures of 1984, and he draws on Doug Pravitz's works, and they still work together even today. So Doug Pravitz is kind of made more philosophical. He had more philosophical articles. There are some interesting disagreements between Per Martin Löf and Doug Pravitz, but I'm not going to that. I think that point that I make is very general. They would certainly agree, or so I believe. So I just quote something that Per Martin Löf says in this book. So he says a proposition is defined by laying down what counts as a proof of the proposition. A proposition is true if it has a proof, that is, if a proof of this proposition can be given. So certainly that's not this classical notion of proposition, right, where people say Frege stressed its independence of epistemic issues, right? That is kind of epistemically laden notion of proposition, which is this intuitionistic notion. Then I just mentioned it in passing, but I think he had this notion of judgment, which is asserted proposition, right? We hold proposition true, we make a judgment. And for Per Martin-Löf, he explained it in many occasions that judgment is in a sense more fundamental. So it's kind of primitive thing is a judgment. And then we analyze a judgment into say proposition and its proof or truth value. So notion of proposition, according to this view, comes from analysis of notion of judgment, not the other way around. Okay. But then he has in his early version of his type theory, which of course today exists in a lot of other versions, but still some core, I think, very much persists. It had 4 different forms of judgment, but I'm not going to actually to list them here and only explain what probably the most basic form of judgment that syntactically just says that A is a little a, or I just lost this column here, is a term of type big A, right? And then Martin-Löf says that there are at least 4 different ways to think about this, right? They are all somehow interchangeable, according to this account. You can think about this term as just an element of its type, right? Or, and that's of course very fundamental for all this logical aspects, and in computer science, it's also what leads to so-called proposition as types paradigm, right? That you may think about your type as a proposition and a term of this type as its proof, which people also in this community call witness or evidence, right? You may also think about this little a as a method of fulfilling intention or expectation of A, right? And that language actually was used by Heyting. They use German word Erwartung for expectation, intention. So I think it's also kind of connects to phenomenological stuff. I'm not going against stuff, but that's a kind of philosophical language which historically has been massively used in this tradition. And that's something that actually Martin-Löf refers to Kolmogorov, and I remind he actually spent a lot of time in Moscow University, so he worked under Kolmogorov's supervision. So you may also think about your term as a method of solving a problem and think about type as a problem, right? And so according to Martin-Löf, all these are just different ways to think about the same formal structure. And even he makes some claims that sounds kind of improbable outside this context. So he says, if we take seriously the idea that proposition is defined by laying down how its canonical proofs are formed, and accept that a set is defined by prescribing how its canonical elements are formed, then it is clear that it would only lead to unnecessary duplication to keep the notion, proposition, and set apart. So you see this formal identity, right? So formal, the fact of sharing the same logical form, Martin-Löf really interprets as kind of essential identity, right? So he says it's kind of superficial that we distinguish between proposition and sets. Instead, we simply identify them. That's treated the same notion. That's his claim of 1983. Okay. Okay. Now I'm going. So that's for explaining what I call this orthodox intuitionist view, according to which problems and propositions are basically the same. Okay, he does the yeah, actually Martinelli does mention problems, right? And but problems we may understand, I mean, we may also probably put the word construction here, right? Thinking about construction in this way that along with the mathematical construction, we have a method of building it, right? So, and so what we have like set or proposition, it's all on the same list, it's just different ways to think about the same thing, according to this view. Okay, and now I'm coming to very, very interesting letter written by Kolmogorov in French to Heyting in 31. Sorry, I have just this Zoom closes for me the year. I think it's 31, right? Just before the publication of his paper. So it's a discussion that preceded the publication. But there Kolmogorov already reacted to Heyting's publication. And so he expresses some sort of disagreement with Heyting as follows. He says that, that's my translation from French. Every proposition P in your conception, says Kolmogorov, is in my view one of these two sorts. Alpha, he says, P expresses the expectation that in such and such circumstances, a mathematical experiment, actually he uses the word experiment, will give a determined results. For example, that an attempt to decompose an even number n into a sum of two prime numbers, p and q, will be successful if all pairs of smaller prime numbers are used. Every such experiment should be, of course, realizable with a finite number of well-defined operations. And then he says there is another sort of what Heyting called proposition. And he says the P expresses intention of finding and construction. So I think he has in mind something like traditional geometrical problems here. And then he says, I prefer to reserve the name of proposition only to proposition of type alpha and call propositions what Heyting calls proposition of type beta simply problems. Given a proposition P, and here I explain the context in a minute. One has problems not P, and that means I'll come later to that to reduce P to contradiction. And what actually Heyting denotes as plus P, and that is modalities, what corresponds to box, I think now, otherwise Sergei will correct me, but this is modality that basically makes from proposition P a problem to prove P. Right, there is a context of that's very interesting in Heyting, and there is also very interesting discussion of Heyting with Freudenthal about this plus, but that's probably for different talk. I just don't have time now, so that's I will skip. Yeah, just a couple examples to see what Kolmogorov just gives an examples of proposition. So he says, just find a quadruple of integers such that that condition of Fermat theorem is satisfied. That's first example. And next example, it's just to show that last Fermat theorem is false. Okay, and so what I think is rather remarkable that it's not the same problem for Kolmogorov, you see, and moreover, he actually says, sorry, I didn't include that. He says that the difference is obvious, even I don't think it's absolutely obvious, right? Because we basically find counterexample in the first place and the second. And I think his idea is that through this first problem implies in this construct the second problem, right? Or otherwise the if first problem is solved, that solves the second problem, but not the other way around, right? Because possibly a proposition could be say, falsified otherwise, rather than it could be also reduced to contradiction, for example, rather than be refuted by explicit counter-example, right? And I think it's very clear. So that actually shows that for Kolmogorov, it was essential to distinguish between problems and propositions. So of course he understood that propositions in this context should not be understood classically, and still he insists that there is this alpha and beta, right? Frankly, what exactly alpha says for me remains a bit unclear, right? So on formal aspect, the things are more clarified by this modality. So what it means that experiment and somehow expectation of determined result. But I do think, I suspect, say, my hypothesis is that what he has in mind, that we might not have here a precise proof, right? We just have this idea that that problem is provable, right? And that's what makes it different, and what will be, again, make it more similar to homotopy type theory, or perhaps I just look on Kolmogorov from this optics of homotopy type theory. At least one suggestion would be that what he calls a proposition, right, that every even number can easily sum of primes, is a kind of, you don't have explicitly proof of it, right? You only have this kind of expectation that certain method would solve your problem, if you want to think about that's a problem. And that's a specific case. It's not the same as, say, just looking for construction of, say, triangle or something like this, right? And again, I think it's interesting historical evidence of the fact that he didn't want to mix up proposition and problem is actually his commentary given in 1985 when his collected works were preparing, right? It's 2 years before his death in 87. So he says then that this paper in question of 1933 was written with the hope that the logic of solution of problems would later become a regular part of courses of logic. It was intended to construct a unified logical apparatus dealing with objects of two types, propositions and problems. And so it's also clear that this idea that you can just use ready-made calculus and interpret it as a calculus of problems, it's still not the last word in that story. So there is kind of project behind, maybe not really completed, right, to build some sort of calculus with these two things, propositions and problems. And that's also interesting remark, which I think explains a bit this difference between this alpha and beta. So he says, for case beta, the difference between P and plus P is not essential, right? So if we have a, say, geometrical problem to, I don't know, bisect an angle, for example, right? So if we just think about P is this problem and plus P just says prove this problem, it's more or less the same thing. However, and that's intuitionistic, of course, right? So we don't have this excluded middle or double negation elimination. However, in case A, P and plus P have different meaning, right? So just have a proposition like say this Bolbel conjecture, right? And proposition that to prove it, right? Prove your goal. It's not the same thing according to Kolmogorov. And on the other hand, in these cases, he assumes that actually double negation elimination works. So it's basically a classical fragment of this calculus, right? Yeah, and I just want to mention very interesting work of our colleague from Moscow, Sergei Melikov, who actually developed already for a while, about 10 years ago, he started actually a kind of system which is strongly motivated by this Kolmogorov calculus, even if it's not supposed to be historical reconstruction. And so what Sergei suggests, actually, he introduces second modality. So we have this modality plus, which Sergei thinks about this plus as actually a way to transform a given proposition into a problem, right? So we have proposition P and problem prove this P, okay? And then he has a kind of dual modality which make in the other direction. So it makes a proposition out of a problem, and if you have a problem P, proposition reads that this problem has a solution. And then he developed, and so his logic for propositions is classical, and for problems is intuitionistic, and then he builds these two things together via Galois connection. And actually his student, what's her name? Nichiporenko, I think she actually defended her PhD and developed this calculus, and indeed interesting. But I'm actually trying to go a little bit in different direction to homotopy type theory, as I mentioned in the title. I discussed with Sergei, he also thinks it's relevant, so he doesn't know yet how to connect his research to, say, homotopy type theory, and that's could be also interesting problem. So it does look like we have a kind of very different interpretations, rather different ways to think about this. Right, and now I make very brief reminder of homotopy type theory, right? And show how it's relevant to that story. So in homotopy type theory, we start, at least that what's historical now, people use some other type systems, but historical just started with Martin-Löf type theory that I just mentioned. And the types and their terms are interpreted correspondingly as spaces and their points. And actually a key role is played by another form of judgment, which is actually called propositional judgment. It just says that two terms are equal, and that's only possible to form if these two terms, say big P and big Q, are of the same type T, right? But then the trick is that we may have different terms of that type, right? And as a proposition, that is a type again, right? And as a type, it has its own terms, which are interpreted normally, and that's what, back to Martin-Löf, so before this homotopy type theory, were interpreted as just two different proofs or evidences of this equality, of that this big P and Q are equal. And the trick is that you think about this P, little p and Q as two different patterns. So you think about big P and big Q as points in space T, and these little ones as a path between big P and Q, and then actually you can continue this, right? So that gives you new equality. So you can wonder this little p is equal to little q or not, and that will give you still high identity type. So you have kind of hierarchy of identity types, which is modeled here by actually a theory of homotopy. So imagine you just have a space, you have points, you have paths, you have homotopy of paths, right? And you have a second order homotopy between homotopies and etc. So what you have is actually in a category theoretical machinery, you translate this as n groupoid on going to infinity, you get a infinite groupoid, right? If you're familiar, say, with a fundamental group of a space, right, you get just groupoid. If you avoid just choosing base point for your loop space, right, you just take all points, all paths, and that is groupoid. But then you add homotopies between properties. It's not only that you look into paths up to homotopy as usual as in homotopy group as well, right? But you just want to look into individual homotopies. And then you identify these up to second homotopy, etc. And that in general gives you that construction of higher groupoid, which that was Grothendieck idea that somehow actually captures your space. So this algebraic properties of this homotopies, no, put it mildly, tells you a lot about your underlying space. That's idea, right, that I just explained, second level, and you continuous as well, right? And actually what people do, at least my observation a little bit from outside in homotopy type theory, so they kind of combine this geometrical language of homotopy theory with say this epistemically laden language of constructive proof theory, right? Of say proofs and propositions, witnesses, and so on. And okay, then the key thing about this thing, it's so-called homotopial hierarchy. So what you observe that not all types are the same. So there is this notion of homotopial level of time. There is of type. There is this simple inductive definition that space is of h level n+1 when its points that path spaces, right? And path spaces are formed just as I just showed when you make this identity type. You say x equal y, and different proofs or evidences of this equality gives you path spaces for this pair of terms. Right, and so we say that space is n+1 if this path spaces is of level n. Right, and then you may, okay, that's a little bit mysterious what is the beginning, but it's kind of just primitive point like in Euclid, but at least of that level it becomes already very clear. So you have say empty set and singleton, right? And these things you think about these as propositions that was proposed by Vygotsky. So empty space is a false and that is a true. And then you have sets, okay? So in sets, just imagine, you may have a path between two given points or not have a path, right? If you do have a path, you say that the same point. You may geometrically think you kind of contract your path into just a single point. And the whole story is whether two points are connected and then the same point or not, right? And so in that sense, you have your path space for sets you have on propositional level. It's just yes or no, connected or not connected, right? But then you get groupoids. You get groupoids just saying it's not only a story of being or being not connected between 2 points, but how connected, right? So you allowed here to have many different paths between 2 points. But these paths, they form sets, right? So you have a set of paths from, say, point X to point Y. That's what happens on level 1. But then you inductively, you proceed and go to 2 groupoids, homotopy, and so on up to omega groupoids. And
now, Andrei, do you have a technical meaning of flat groupoids, or you just?
It's a kind of jargon. No, flat meaning that it's 1 groupoid. It's not 2 groupoid, right? So okay. You have only
only objects and
theoretical parlance, right? You have objects and you have invertible morphisms, but more than one generally, right? You have some set of morphisms. So you have Hom sets, okay, right. Here. And here it's like 2 categories. So you have all of that, but you also have you have homotopies between your paths, right? So it's kind of three kind of things: objects, morphism, and two morphisms. Everything invertible. So that's two groupoid and so on. Okay.
Yeah. I just want to know what the word flat. Okay, fine. I understand.
So I think one important thing, and it's not always mentioned in the position, that's actually hierarchy is it's not how say these levels are not equivalent classes. You see, it's kind of cumulative in a bit strange way. It's kind of cumulative from if we print it in that way, that from below to down up, right? How to say up down, right? And that in this sense that of course if you have some k type, right, of level k, then it's also n type for all n bigger than k. That say every proposition is a set, as I just explained, empty set or singleton. But not every set is a proposition, you see. But on the other hand, every set is a trivial flat groupoid. So you may just have, okay, I don't have paths, and it's still a groupoid, just kind of trivial groupoid, and so on. So, right, and actually, I'm going to use this remark in what follows. And in the other direction, if you want not to rise your level, but to diminish it, there is this operation called truncation for geometrical reasons, right? And the idea is that actually you may simply not distinguish your paths or say path between up to a certain level. No, actually what we are going to use is this propositional truncation, okay? When, for example, I have multiple proofs of say proposition, what is otherwise a set, right? And I kind of only interested in the question, is it empty or not empty? So I'm no longer distinguish between different elements of my sets, okay? And that's would give me propositional truncation. So I have a set and it has many different elements, but then I truncate it in the sense that I only give yes, no answer to question it's empty or not empty, okay? And that's how I get, say, proposition out of, say, set or any higher order homotopy type, right? That's idea. And of course, this whole thing is completely at odds with what Martin Löw thought about his system, you see, because what I just quoted, right? So in a sense, if we, how say, give this homotopy interpretation kind of objective meaning, and I think we should do that, right? Because this homotopy interpretation is not just how we can interpret it as you want. Actually, what is thinking that this homotopical hierarchy, it's already there syntactically. It's this homotopy theory is rather just helps to understand it and realize it, to represent it, because otherwise it's kind of combinatorics, which is absolutely untreatable, right? And by this geometrical means, we more or less have a kind of picture how it works. So it's still there. And if we also, of course, believe this kind of naive interpretation of this sort, right, that we should think about this H level -1 as proposition, as sets, things looks natural, but of course it's not very formal, right? Because it's not set of Zermelo-Frankel, it's kind of discrete point space, right? But still, if we believe all this, we may say that Martin Löw just was mistaken, and this different thing, they really are different also syntactically in this system, even if it was not intended at all. Okay, and on the other hand, at least I submit that it supports Kolmogorov's view okay, he didn't have in mind this whole hierarchy, but at least he separated problems and propositions. And problems, okay, there is no problems in this hierarchy, but I think about all these higher homotopy types as a kind of higher order construction. And construction, I think about construction as a problem in the sense that it comes with a method of constructing it. So construction is not just a final result, right? Is a kind of procedure which is given by rules of type theory in that case. So I think it's kind of seems to me natural, at least, to think about these things as a problem, as problems of different levels, right? So that's so if we saying, okay, let's put these views really different. Either we want to put everything together, or we want to separate, say, propositions to separate them from more general problems, then this discovery of homotopy type theory, that really gives some weight to Kolmogorov's view. But also, of course, it supports that they still have this, how to say, they share a common structure also. And that was stressed by Martin Löf. But this fact of sharing common structure that does not actually prevent them be different also on syntactic and formal level. That's what I want to stress. It's not just a matter of wording or someone's preferable way to think about this. It's really in the theory, even if it was not intended to begin with. Okay, now I'm trying to be quicker. I have this part of negated problems, which I think is very interesting and kind of more problematic. At least I don't quite understand. So he says, okay, negation problem is usual as in intuitionistic logic, derived contradiction, okay? And of course, there is some problem that is a propositional notion, contradiction, right? Contradiction is like A, non-A together. And that looks, be nods with the strategy to, how to say, not avoid this reduction of problems to propositions, right? But actually, yeah, there is this suggestion just to find kind of counterpart of standard falsum for problems. And there is this paper by Zans who called it panacea. So by analogy with X falso, we have this kind of problem that makes solvable any other problem. Yeah, but I just mentioned it, I know. But then actually, Kolmogorov tries to explain, and then I think things becomes even more cryptic and but also more interesting. So he said that not A, defined as above, right, should not be read as prove the unsolvability of problem of A. You see, it's already in the general case. If the unsolvability of problem A is considered as a completely defined notion, we only obtain that not A implies unsolvability of A, but not the other way around, not the converse. If, for example, it were proved that the realization of, well, ordering of the continuum is beyond our possibilities, it would not be possible to assert that the existence of such a well ordering implies a contradiction. Right, so we have this proposition problem A has a positive solution, implies contradiction, then A, of course, is unsolvable. But according to Kolmogorov, the converse does not hold. And so, and here I'm actually not sure if we take something like intersection of given angle, would be that also example or not? Should these, our possibilities referred to by Kolmogorov in this quote be understood in kind of absolute sense? It's how Brouwer, for example, had it. Or it could be matter of convention, like a ruler of compass. Yeah, but say also remark, if we actually take the special case of problem, which has a form proof proposition, right? We may call it propositional problem. then the unsolvability of A does not imply that A is contradictory. That is Gödel incompleteness, syntactic incompleteness, right? But then it remains open, and I don't have answer, but I think it's maybe some of you have a straightforward answer. How that would work in case of problems, right? That's kind of incompleteness. So we so existence of solution does not imply contradiction of a problem, but still problem is unsolvable, right? Yeah, and it also goes along with the interesting remark that is for the second part of the paper, where he really criticizes. It's more philosophical, so there is some formal stuff in the first part, but second part is purely, let me say, philosophical or speculative. And actually, what Kolmogorov does, he criticizes this notion, standard notion of intuitionistic negation, by saying that it's not intuitionistic enough, so to speak, not constructive enough. So he says, Brouwer suggests a new definition of negation, namely A is false, should be understood that A leads to contradiction. Thus, the negation of proposition A is transformed into existential sentence. There exists a chain of logical inference leading to a contradiction if A assumes to be true. But its existential sentences were profoundly criticized and, in a sense, banned by Brouwer. So that's kind of incoherent. This is the argument. And then he makes a remark, I just paraphrase rather than quote in that case. He says, if one takes into consideration only problems such that its negation is constructively provable, right? Then we have the law of excluded middle. And so we are back to classical propositional logic, so we somehow lose our subject matter. So that's also is not a solution. And then I just, I was thinking, would it be in this HoTT framework make any sense? But apparently, at least I also spoke to different kind of experts in HoTT, and so I came to conclusions that not. And this is because we have a single empty type, right? Which is propositional, of course, just false proposition, kind of generic false proposition, but having in mind what I said about this cumulative character, right? It also may qualify as a higher type of any order, right? But still it's always the same. And to realize this idea in HoTT, we would need to have kind of hierarchy of empty types. So we would have kind of empty types for each homotopy level, such that, say, it would still work from bottom up, right? So if things are contradictory, we cannot do them, of course, right? But it could be possible that we might not do them also for some other reasons, not because of logical contradiction. And that's, I think, historically, it's also a rather old topic, and that was actually from Heyting's dissertation, which was not on logic, it was on geometry. And there he introduced what he called as a partners relation. So that's, again, idea that we may have about, say, non-identity, not just kind of, how say, not in that way by deriving contradiction, but just introduce this apartness as a primitive relation, kind of ignoring that negative character. So we have it semantically, but syntactically we just introduce it. Yeah, we have negation. That negation just gives us standard identity, but then we have this crucial third axiom that says that actually A is apart from B, implies that for every C, it's either apart from A or apart from B. And then he develops this intuitionistic theory of geometry on that basis. So it's not just intuitionistic logic used as a kind of background logic for geometry. It's also kind of specific intuitionistic, say, relation, like apartments relation, what he's doing. And there is some more recent work, but probably, again, that I say for another talk, maybe then people also try to reproduce Heyting apartment, but like, say, in modern technique. So I think it could be interesting project, probably, right, to develop some sort of type theory with this homotopical interpretation, which would support this feature. And I think it could be very useful in a real life, so to speak, because in real life, unsolvability of problems typically resource-related issue, if I understand anything about computer. And it happens, but it's not maybe typical. It's a really matter of logical inconsistency. So probably logical inconsistency should not be just the only reason for negate something, right? It could be some, say, weaker, probably we should keep it as the strongest reason possible, but could be some weaker reason, which would still be sufficient in a certain situation. No, so I conclude, so I think Kolmogorov's idea to distinguish between problems and propositions and build unified logical framework for both for problems and propositions without dispensing difference. If we consider this again against the intuitionistic strategy to merge these things, then we may claim that this Kolmogorov's idea receives an unexpected support from the homotopical interpretation of Martin-Löw's constructive theory, which really goes kind of against Martin-Löw's original intention, at least back in 1883. And second, just I think that there are still interesting ideas which, as far as I know, and as far as I understand, are not yet fully realized in formal settings. So would be some interesting work to be done, in particular, probably with HoTT. Okay, thank you.
Thank you very much. Very nice.
Yeah. Should I stop sharing or?
No, because we might want to go back on the things. Can you see everybody?
Listen. Yeah, now I can.
Oh, okay. Anyways, any questions? I just have a quick thing. Is there like some type of truncation between problems and propositions?
No, say truncation. Yeah, it's a standard notion in
HoTT.
Homotopy theory, right?
Right.
In HoTT, right. Then the rest is, of course, interpretation. But my understanding of high types, right? That's okay. Everybody would call them construction. But if you say construction, I may replace that by problem, right? Because construction comes with a problem to construct it, just like a theorem comes with a problem to prove it. Right. And actually, the two things are related. That's not just like two words. It's how the construction may prove particular proposition, right? And so you need truncated to get to your proposition. So propositions are always kind of at the bottom. It's level -1. So at least in that framework, it works like this, right? You truncate everything, you come to proposition. Probably it's not very intuitive because it just, like to a single proposition, right? Because if you have a construction in normal life, you may have a lot of different proposition about it, right? And here you just comes to kind of canonical. And that's probably a problem for this interpretation. I think.
So given a problem, if you truncate it, you get a proposition, and the proposition is true or false, meaning if there's a solution to the problem or not.
Right. If you had but here it's kind of interesting because we are talking about kind of, how say, fake constructions. You know, there are examples in Euclid, for example. It's very interesting. He has a theorem that says that two circles intersect maximum 2 points, right? Right. And to prove it, he proves it by reductio, and he makes a how say, he considers a construction of two circles intersecting 4 points, and then he shows that that's impossible. So you see, you kind of have a construction and you don't have it. So finally, your thing is empty when you analyze it, and so your proposition is false. But if your construction is good, so you get your proof.
Very nice, very nice. Nice. It's a nice connection. Any other questions?
A lot of comments, but not really questions. So let's give this way to questions.
Okay, so any comments, please?
Very nice talk. I'll jump in first. I've just got a couple in terms of references where I think, I mean, connecting this to HoTT is very nice. I don't think we need to go all the way to modern HoTT to spell out some of what you're saying, just sort of as a historical point, right? So the calculus of constructions already introduced a distinction between the universe of propositions and the universe of types. It didn't go further than that, a bit prior to HoTT, I think. You can then answer once I'm with this genealogy and tell me, no, what this is why HoTT's better. And also the notion of truncation is predated by squash types, which were in the Cornell system, and then the Audi-Brouwer formalization with the box modality. All of which is to suggest, I think you really, to capture at least the historical stuff, which I think it's very neat how you capture and use it to elucidate, I think you don't need maybe more than 2 levels. And those are the 2 levels that we've had around a bit prior to HoTT. HoTT completes the picture and maybe makes it nicer, but I'd be curious, I guess that would be a question, if there's something we get by going beyond what we get with, say, the prop universe and truncation in the higher levels, that's also suggestive in casting light on these older problems.
Yeah. No, I think what is interesting in HoTT, that in a sense it was unintended, and so that probably give reason to talk about kind of objectivity with some kind of epistemological sense, because you say in the calculus of construction, right, but that is made by hand, so to speak, right? That's a difference. Of course, it's made in kind of very coherent and nice way, but here it just comes from mathematical research without any particular, philosophical ideas. Or more precisely, Martin Löw had a strong philosophical agenda, but then kind of purely mathematical development made important corrections to this agenda, and that's, I think, it's interesting.
Sergey, you want to go?
Yeah, I can go. Yeah. Well, first, Andrei, I noticed your distinct French accent, which I heard from you before, which is understandable, and also I cannot avoid thinking that it's a very deep night in Paris, or wherever you are in France.
Yeah.
So my sympathies. Yeah, you really. So it means that most of you see that this gentleman actually sacrificed a lot to give this talk live in your seminar.
We apologize.
That's life. And indeed, there was I just want to zoom on one specific problem, which was discussed here. It's the problem of intuitionistic negation, or the constructive treatment of negation. And of course, it was a well-known weakness of the of the naive BHK semantics understood in Heyting sense. When you look at this ABC, so this the bullets or the clauses of how to read intuitionistic connectives and quantifiers, then you'll see that, and if you try to analyze them, these witnesses as mathematical constructs, for example, realizers, then you end up with a quite unsatisfactory picture for negation. So negation is as it was shown and it was noticed even in this natural language communications with the founders, including Kolmogorov, Heyting, and with Brouwer on the back in the background. It was known. It was a known weakness of the constructive semantics, in particular in realizability semantics. In particular, if it turned out that if the negative sentence is realizable, then anything is a realizer, which is nonsense. That means that there is no real causality connection between the realizer and the realized sentence. In particular, yes. And I wish to recall the name Kreisel. He came it's one of the several famous cases, I can name two, where Kreisel had absolutely brilliant ideas, but the technical realization of these ideas was a failure. In particular, it was so-called Kreisel's second clause. He noticed that the naive understanding of BHK, reading of BHK implication, A implies B, as it's a construction which, given a proof of A returns a proof of B, is not enough. And this is what caused the first place. It was caused the problem with reading of intrinsic negation, which is a special case, maybe regarded as a special case of implication. So the problem was with implication. So Kreisel famously added informally at that time the second clause, saying that not only we have the proof of the constructive proof of implication is the intrinsic proof of implication A implies B is a construction which, given the proof of A returns a proof of B, but also a proof that this construction generally works. Without this provisor with a second layer of the thing, it just doesn't work. And but with this thing, with the Kreisel's second clause, it kind of works. And the easiest way is to understand how this works. I'm sorry, I wish I could. We can do some writing, but since it's very small pictures, I try to just say them. Let's consider the negation not A, where A is a proposition. So
well, 1 second. Do you mind if I stop the recording or?
No, that's fine. Absolutely.
Okay, this is a little technical and okay.
Yeah.